All right, you guys. So this is the second time I've recorded this. So that's special. We are going to go over modules 24 and 25. Just a reminder, you did not need to read 25. Hopefully, by this point, you have read, taken notes on modules 24. You took the reading quiz because we're just going to go through that real quick. Make sure that we're feeling groovy with all things hearing and sound and auditory related. And then we will talk briefly about the other senses. So I suggest just having your notes out while we kind of go through this stuff to give yourself any clarity, those retrieval cues to help you remember the differences between theories and parts of the ear and that process and whatnot. So have your notes out. We'll go through your reading quiz and then talk the other senses. Okay. So the first question on your reading quiz: frequency is to pitch as amplitude is to loudness. So this is referring to the shape, size, and speed of our sound waves, right? We know that sound waves enter our ear, create vibrations in our eardrums and our inner ear, and then are transmitted or transduced into auditory impulses, neural impulses that are sent down the auditory nerve. Frequency is associated to speed. So really, 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 really fast waves are going to be interpreted as high pitched, and really, really, really slow waves are going to be associated with low pitch. Amplitude is wave height. So really, really, really high waves are going to be very loud, and really, 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 really short waves are going to be very quiet, right? This question is really getting at, one, it's an analogy question, so good practice. But two, it's just getting at the fact that how our mind our ear transduces these sound waves is based on the shape, size, and speed of the waves coming in. And then from there, our brain is able to interpret different sounds, pitches, and what have you. Yeah. Number two, the hammer, anvil, and stirrups are small, tiny little bones that amplify vibrations made by the eardrum. They exist in the middle ear, but we will get to that a little more when I look at the diagram of the ear that you will need to know for Monday's matching test. So bear with me. We're just going to cruise right through this and we will revisit. Transduction. This is the transduction process. You know that word transduction. It's when we take an actual sensory stimuli and turn it into neural impulses that our brain can interpret. For the ear, you will need to know this process, right? Vibrations made by the eardrum are transmitted to the cochlea to be sent down the auditory nerve and directed by the thalamus to the auditory cortex in your brain's temporal lobe, right? We know our temporal lobes are associated with auditory input. And so just kind of keep that in mind. That's the final location that these impulses end up. But when we're looking at this process, right, waves come in, the eardrum starts to vibrate. Those vibrations are amplified, like I mentioned, by the hammer, anvil, stirrup, and they make the little hairs on the cochlea move. And the movement of those hairs instigates a neural impulse to be sent down the auditory nerve to be interpreted by the brain. Okay, this is the diagram that you will need to know for Monday's matching test. It's literally this exact picture. I will have you refer to your pink terms list for the exact parts of the ear that you will need to know. You will not need to know the process. You are just labeling this ear. You do not need to tell me function. You do not need to tell me anything except for where it is located. Okay. On the AP exam or on our test, even, you aren't going to be given like a diagram that you need to label. With that said, knowing this process and knowing kind of where these things exist is going to be beneficial to you in your understanding of that transduction process. So I'm going to talk you through it real quick. I know you read about it. I know you have these different parts of the ear kind of written down in your notes, but I'm going to talk us through this process just to give us clarity, right? So our outer ear, right? The outer ear is what we can see, the actual like flesh and cartilage that's on the side of our head, right? That acts as a funnel to collect sound where it hits the eardrum. The eardrum is kind of like the barrier between our outer ear and everything else, right? It acts as a drum, it vibrates. And once those vibrations get into the middle ear where our hammer, anvil, and stirrup are located, those three little bones are going to amplify that vibration so that by the time those vibrations reach the cochlea, this little seashell looking thing, we are able to have those little hairs pick up vibrations and transduce them into neural impulses. So just kind of note, right? This, oops, I don't know what I'm doing here. I'm just gonna, our cochlea is right here. It looks a little bit like a seashell. Inside of it, there is fluid and little, what they call cilia, little baby hair cells that as they move and their movements are different, whether they're really fast, really slow, right? That's going to determine the type of impulse that is sent into our brain to be directed by the thalamus, then to our temporal lobe to be perceived as pitch or whatever. Okay. So this is what you need to know. You are just labeling. You do not need to know function. On Friday, when we are back in school, presumably, we will go over the eye portion of what you will need to know. For now, you have your ear. Question number 4 is looking at hearing loss. You're looking at the difference between sensory neural hearing loss and conductive hearing loss, right? I always think about sensory neural. It's damaging our ability to transduce those impulses, whether it's damage in the cochlea or to the auditory nerve. Conductive hearing loss is more like external, a ruptured eardrum, any sort of like blockage in the earway. Those would be conductive hearing losses. What I'm going to do, I'm going to have us watch a video for both of these. And while you are watching it, again, you have your notes out, you have the definition of sensory neural hearing loss and conductive hearing loss. I want you to just jot down a few examples of each as you watch these really, really short videos. Okay. So here is the first one. Here's sensory neural hearing loss.
In our inner ear, we have a lot of tiny hair cells that move and pick up the sounds that we hear. The movements are then converted into signals that are sent to our brain. Sensorineural hearing loss results from damage to or reduction of the number of tiny hair cells in the inner ear. One of the causes is aging. We all lose some of the tiny hair cells in the inner ear as we age. Another major cause is noise. Noise can damage the hair cells in the inner ear. Diseases such as mumps, meningitis, and Meniere's disease can result in a sensorineural hearing loss. Certain drugs like aspirin, cisplatin, quinine, and some antibiotics, as well as certain types of chemotherapy, can also cause a sensorineural hearing loss. Sensorineural hearing loss can be inherited, and finally, you may lose your hearing ability due to head or ear injuries. A sensorineural hearing loss cannot be cured, but people with a sensorineural hearing loss may benefit from the use of hearing aids. You can find out more about sensorineural.
Okay, so there you have your sensory neural hearing loss, right? Disease, aging, injury, medications, those things are what we see damaging that inner ear and the ability to transduce those vibrations into neural impulses. They cannot be cured, but they can be addressed or treated with the use of hearing aids and other cochlear implants, other types of medical intervention. So hopefully you have some of those examples written down. Now we're going to watch conductive hearing loss. So again, you're jotting down examples of how we might get conductive hearing loss to give ourselves kind of a trigger to remember the difference between the two.
What is a conductive hearing loss? The outer ear is the external part of the ear. It collects sound waves and directs them into the ear through the ear canal. The middle ear transmits the sounds from the outer ear to the inner ear. A conductive hearing loss occurs when the ability to conduct sound from the external and middle ear into the inner ear is reduced or lost. One of the most common causes of conductive hearing loss is a blockage in the external ear canal, for example, because of earwax. Other causes of conductive hearing loss can be infections of the ear canal, a damaged eardrum, very small ears, cysts and tumors, or even foreign objects in the ear canal. A conductive hearing loss can also be caused by diseases, damage, and physical changes in the middle ear. Luckily, many cases of conductive hearing loss are temporary, and most can be cured. However, if you think you have a conductive hearing loss, you should contact your family doctor.
Okay. So you have the difference between those two. Hopefully you have some examples to kind of cue yourself, to prime yourself to remember the difference between the two. Okay, moving on. Good. Okay, so this is kind of the last big takeaway when we're talking about hearing and the transduction process, right? How does our brain interpret different pitches and sounds and audio quality things? There are a couple of theories that exist when we are talking about this process, okay? So what I'm going to do, I'm going to draw us a little cochlea here. Right here is our cochlea. Wow, Miss Ellis, you're such a talented artist. Okay. And on that cochlea, in the inside, we have little baby hair cells, right? I mentioned this. Little baby hair cells. These are called cilia, and they exist all throughout our cochlea. Woohoo. Look at that. Beautiful. Now, according to frequency theory, that's the first one listed here, the theory that the rate of nerve impulses traveling up the auditory nerve matches the frequency of a tone, thus enabling us to sense pitch, is what I explained in the transduction process, right? If the frequency is really, really fast and those little cilia, those little hair follicles, those little hairs are moving really, really fast, our brain will send a neural, or our ear down the auditory nerve will send a specific neural impulse that says this is fast, this is high pitched, right? If they're moving really slowly, if the frequency is very low, right, it's going to be interpreted as high pitch. Now, with that said, there are those who kind of believe in this idea of the place theory. So I'm going to skip to number 3. Place theory essentially says that we link the pitch we hear with the place where the cochlear membrane is stimulated. So for example, if you hear an A sharp, right, you might have this area of the cochlea that gets stimulated. And so your brain says, oh, that's an A sharp. I mean, those of us who don't have perfect pitch don't do that, but we're like, oh, that's a high pitch or whatever. And then you hear a B flat, right? And maybe it's this part of the cochlea that's getting stimulated, right? And if that's the case, our brain is like, oh, that's a B sharp, that's a lower pitch or whatever, right? And so place theory says that the location on the cochlea being stimulated is associated to our ability to differentiate between pitches. Okay, I know this is quite the beautiful drawing for you guys, but it's what we've got, right? So frequency versus place theory. Now the volley principle, I wouldn't put too much time, energy, and effort into, but essentially what this is saying, it's related to our frequency theory in that, like, when we get to really, really high pitched sounds, our neurons are unable to fire quick enough to send that interpretation, right? So an individual neuron can't fire faster than 1,000 waves per second, but neurons can alternate firing to sense sounds with frequency above 1,000 waves per second. So this is basically our brain's kind of hack in order to pick up on those higher frequencies. And so they basically just alternate firing so that they can trick our brain into perceiving a faster frequency, if that makes sense. Again, don't worry too much about the volley principle. Just understand that it's kind of like our brain's way of giving itself the ability to fire faster than naturally it actually can. So with that, how do I erase this? I'm going to erase this. Yeah, get out of there. We don't need that. Okay. The last piece of the puzzle is sound localization. And I know I've said this before, but it just boggles my mind what our brain is continuously and constantly doing, right? Not only are you like listening to what I'm saying and comprehending it and probably writing some of it down, figuring out what is important and what you can just kind of listen for. You might be doing some other stuff at the same time as you're listening to this lecture. But usually during this slide, I'll get up, you guys, I'll have you close all your eyes and I'll get up and I'll walk around the classroom and I'll talk and I'll talk and I'll talk and I'll be like, wow, the brain, this is so cool. And then I'll stop like in the back left corner of the room or someplace, maybe in the middle of the room. And with your eyes closed, I have you all point to me, and all of you can do so effectively. You can't see me, but you know where I am based on where the sound is coming from. So not only are you doing all these things, right, for the lecture purpose, but you are also, your brain is doing like really fast math to determine the difference in timing between what your left and your right ear are taking in, right? Not only like when the sound actually hits each ear, but also at the amplitude or how loud each ear is. And it's like beep, boop, beep, boop, beep, boop. Based on the difference between right and left, I know that this sound is coming from wherever, right? God, that's crazy, crazy talk. Okay. So that is what I have for you in regards to hearing module 24. Okay. Check. We did it. We are moving on and we are going to look now at module 25. Again, if you did not have your notes out for that whole thing, you should have. But if you didn't, definitely take them out now because you did not read module 25. And there are a few things that I need you to kind of take away from this module. Yes? If you don't have your notes out, pause the video, take your notes out now. Ready? Go. We are going to talk about the other senses very briefly. But we're going to get like a basic overview of each of them. Ready? Touch, taste, smell, kinesthesia, and the vestibular sense. That is where we are headed. The first thing we're looking at is touch and pain, and that is through the gate control theory. Okay, this is kind of a long-winded definition. This is the definition from your textbook. It says, the spinal cord contains a neurological gate that blocks pain signals or allows them to pass on to the brain. The gate, quote unquote, is opened by the activity of pain signals traveling up the small nerve fibers and is closed by activity in larger fibers or by information coming from the brain. This is pretty sciencey, and you really won't need to know the nitty-gritty details of it, but you should know big picture that our experience of pain is influenced by either small or large nerve fibers sending messages along our spinal cord. Okay, that's the basic takeaway. Why would our larger fibers close that activity, close that communication process? Well, if we were doing something that we were focused on, you've all probably, maybe if you're somebody who plays sports, maybe you've experienced this, right? Where you're like in a game and you twist your ankle and it hurts and you're like, shoot, I sprained my ankle, but you keep playing because you're focused on the game, you're running up and down, you're passing, you're doing whatever. And then after the game, you're like, shoot, that really hurts. And the pain actually like kicks in. That is gate control theory, right? Our large fibers are like, not right now. Don't worry about the ankle now. We're doing something else. We're focusing on something else. Our energy, our attention is elsewhere, right? But then once we stop playing, our small nerve fibers kick in and it's like, but actually your ankle hurts real bad. So we will revisit this in a video in just a sec. So don't get too bogged down in it. Big picture, spinal cord is in control of sending pain signals to our brain. Yeah. Taste is an interesting one. And I always like to look at it through the lens of evolutionary psychology because like, why do we taste? What is the, like, what's the benefit here? We don't like, there really isn't all that much. Like we eat so that we live and survive. We get the energy we need to do the things that we need to do, right? So why do we have all these different taste buds? evolutionarily speaking, it has been beneficial to the human race to know that things that are sour or bitter may be poisonous or toxic. So historically speaking, if you try like a new berry and it tastes icky, right, you're probably like, maybe not for human consumption, right? And so you don't eat the berry, you don't get poisoned, you don't die, right? Remember, evolutionary psychology, always referring to survival, not dying, and reproduction, right? Having the sweet taste is an energy boost, right? Being able to sense out things that are going to give us a boost in our blood glucose levels. Sweets, salty, we need that salt for nutrition, for water retention, whatever it might be. And lastly, umami, which is that savory flavor, helps us determine protein, right? So if you're looking at an evolutionary perspective to why do human beings taste, right? To maintain nutritional balance before all of the Weight Watchers and like all of the labels on boxes and foods and where you could get your like exact nutritional breakdown. Like before all of that existed, people just needed to figure out like what did their body need? And they did so through taste, right? And if their body was craving umami, they probably were low on protein. Kind of interesting. We will do this when we're back in school. It's super interesting. You get like a little slip of paper and you lick it, and some people are super tasters, some aren't. But I won't go into super detail here because we'll do that together as class. Lastly, we have our sense of smell. Interestingly enough, smell is the only sense that isn't processed through the thalamus. Say it louder for those in the back. Smell is the only sense that is not processed through the thalamus, right? It goes directly to the higher regions of the brain where smell is interpreted. And one thing to note that's going to be really important is that the sense of smell is also referred to as olfaction. Okay, it's also referred to as olfaction. You'll see olfactory bulb, olfactory nerve, those listed on this diagram here. But if you see like olfaction on your AP exam or on your test, right, and you don't know that it's the sense of smell, that could be confusing. So definitely take a second and write down that sense of smell is the same thing, synonymous with olfaction. Another interesting component of smell is that its location is, and you can see this in the diagram, is located right above our hippocampus. And that is why we have such strong smell associations with memories, right? You all probably have some sort of smell that reminds you of something. Maybe a perfume or cologne reminds you of a family member or a significant other. Maybe the smell of snickerdoodle cookies reminds you of grandma. Maybe the smell of freshly cut grass reminds you of one time you won the championship baseball game. Whatever it is, we have really strong associations between smells and memories. And that's because their location is so close. They're actually practically touching in our brain, that smell is a really strong trigger for memories. Kind of interesting. So we have touch and pain, taste, olfaction or smell. And we're going to tie it all together with this video before just briefly looking at the difference between kinesthesia and vestibular sense. So watch this, jot down any clarification that you need on that gate theory or these other senses. And then we will finish up our lecture very briefly when he's done.
What's up, everybody? I'm Patrick Kelly, and today we're talking about pain. I'm not talking about my dad never brought me to soccer practice when I was a kid kind of pain. I'm talking about real physical injury kind of pain. But to do that, I'm going to need you to think about the last time that you got a good bump on the arm or a shinner, something good that left like a nice bruise. And unless you had immediate access to an ice pack, there's a good chance that you put your hand on the injury spot. Not because you needed to stabilize the injury, but because something in your brain knew that that would make it feel better. And it's true. Putting touch on an injury site can mask the pain. But how does that work? And we'll get to that. But first, time for the big picture. Pain is just a sensation. You were probably taught the 5 senses back in primary school: vision, smell, taste, touch, hearing. Pain isn't on that list. That's because the idea of senses is actually kind of vague. They leave a lot of information out. But if we want to get a deeper look into what actually happens, we can study the physiology of the nerves that make up the anatomy of each of those senses. Your tongue and nose might be responsible for the overall sense of taste, but each taste bud is more specialized for a specific taste. like the taste buds for salty or for sweet. That's because they contain chemoreceptors, nerves that detect chemicals like the ones that give off flavor or smell. At the cellular level, these are highly specialized cells, but collectively, they make up the overall sense of taste. The same thing happens with the sense of touch. We can tell that a blanket is both soft and warm, or that a knife is both sharp and stiff. And it's all because we have different kinds of nerve endings in our skin that signal for different types of touch. And we can divide those into 3 categories. We have thermoreceptors that detect temperature, a bunch of different mechanoreceptors that detect mechanical pressure or distortion. When you think of the sense of touch, you're probably thinking about what these nerve endings detect. And just to give you an idea of how specific these nerve endings get, we have different nerve endings for low frequency vibrations and other ones for high frequency vibrations, some for sustained pressure and some for just tension in the skin. They're all really specialized cells that together make up our overall sense of touch. And finally, we've got nociceptors that send pain signals to our brain. Anytime we get a signal from one of them, we call that a noxious signal. Anything else is innocuous. If you've seen this diagram before, you're probably familiar with structures like the epidermis and the dermis, but never really knew that those mechanoreceptors were hiding in there the whole time. Now, that diagram is just the surface. That's the point where the outside world meets our nervous system. Each one of those nerve endings is connected to a nerve, but not all nerves are created equal. The nociceptors tend to hook onto something with a little bit of a thinner diameter, while the mechanoreceptors tend to have a thicker nerve. All right, let's assume for just a second that you get punched in the face. Immediately, those nerve signals are just signals. They haven't gotten registered in the brain as, hey, I just got punched in the face. That first part, getting punched in the face and then those nociceptors getting stimulated and sending signals to the brain, that's the process of sensation. It isn't until the brain picks up on what's going on and interprets it that you are now in the process of perception. Now your brain has made sense of everything and can say, hey, I just got punched in the face. And for something painful, those noxious signals travel to the thalamus and then to the somatosensory cortex to get interpreted a little bit further. And that pathway makes enough sense to me, but something stuck out while I was researching for this video. Specifically, like, how does your body tell what gets coded as pain in the first place? I mean, you can shake somebody's hand and it would be fine, but that same size hand can put a death grip on you, and that is painful. But then how does your body say, this is fine, but this hurt? Well, that's exactly what researchers Melzack and Wall investigated in their 1965 article in the journal Science. See, up until then, there were 2 main theories of pain: the pattern theory and the specificity theory. Now, there were other pain theories at the time too, but these were the ones that the research team outlined on their paper. Melzack and Wall looked for a way to tie together the pattern and the specificity theory, but also try to incorporate our own psychology and perception of pain. And that's where the gate control theory of pain comes in. Remember how earlier I was talking about rubbing injuries to mask the pain? Once you get hurt, those nociceptors send signals towards your brain so it can be perceived as pain, right? Here's what Melzack and Wall proposed. Any nerve signal could go to one of 2 in-between destinations while it's on the way to the brain, either to transmission cells that would pick up the signal and take it to the brain, or inhibitory interneurons that would make the activity less intense. For those interested, this happens in the dorsal horn of your brainstem in an area called the substantia gelatinosa. When just the noxious stimuli are coming in, they'll turn down the inhibitory interneuron, which lets them bust through the transmission cells on the way to the brain unhindered. And I know the wording can be a little confusing. So when we're saying decreasing the inhibitory interneuron, that's kind of like a double negative. So that's really meaning that it's increasing its ability to go through the transmission cells. Going back to the example of getting punched in the face, when you rub your face because it hurts, the nerves attached to those mechanoreceptors are actually increasing the inhibitory interneuron on the pain signals. And this is where they got the name gate control theory. Your face is still giving off signals for pain, but by stimulating those touch receptors, you close the gate, which kept the pain signal from reaching your brain. But you can also close the gate from the other direction. Gate control theory says that messages coming from the brain can shut the gate on noxious signals as well. So if you just stepped on a Lego because you were trying to save a baby from a burning building, you might not notice the pain until you knew that you were safe and out of the fire. And hopefully you returned that baby safe. Not every form of pain relief uses this pathway though. Medications and anesthesia use completely different paths. Now, obviously something super painful like a broken bone is going to overpower any mechanoreceptor stimulation. But for your minor bumps and bruises, it's nice to have some pain relief, and the gate control theory of pain offers that. Thank you for watching.
All right. Thank you for watching, everyone. So again, I like that video. It kind of pulls everything back together in terms of sensation and perception, and gives you just further insight. Again, that went into a little more detail than you will need to know about the gate control theory. but for some of us, that is helpful to kind of get a better sense, big picture of what it's saying. So lastly, this is the last slide here, just differentiating between kinesthesia and the vestibular sense. I will say the vestibular sense was on last year's AP exam FRQ, and my kids got it. They crushed it. A lot of kids had no idea what this was. So let's clarify, because it is worth noting, right? Kinesthesia is our movement sense. It's our system for sensing the position and movement of individual body parts. Oops, typo, body parts. So this is why we can walk with our eyes closed, right? I know where my feet are. I don't have to see them to know that they are walking. Same thing that if you close your eyes right now and stick your hands out either direction, have your pointer fingers, and try and touch your nose, right? We can do that. We know where our hands are, where our fingers are, where our nose is. We understand the position of individual body parts, okay? That is kinesthesia. The vestibular sense then is also related to body movement and position, but it's more about whether or not we are upright, right? Like the actual like positioning of our entire body. And this comes from our head position in the semicircular canal fluid. So for example, imagine having like a glass of water. If you have a glass of water and you tip it to the side, right? The water stays horizontal to like the floor or the table or whatever, right? No matter which way you tip it, the water stays flat. That is what's happening in our ear, in that fluid that's in our cochlea, that semicircular canal fluid, that when we tip our head to the right, it stays flat, but our semicircular canals are able to perceive like where that water line is, and it knows where our head is tilted. People who suffer from like seasickness, it's because of this vestibular sense, right? The semicircular canal fluids are moving, but like their vision says they're still upright. And that messes with their senses and makes people feel nauseous or get headaches, okay? So kinesthesia, individual body parts. Vestibular sense are like full-on body position. Are we upright or have we fallen down? Okay? So that is what I have for you. Usually with this lecture, we watch this episode of Mindfield, but it's not a necessary piece of information. If you're interested, episode 6 of Mindfield, it looks like Touch. It has some like really cool experiments that you can do. It's just interesting. So feel free to watch it if you want, if you're interested. But other than that, that is kind of what we have for today's lecture. With that said, Friday, we're going to go over vision. So be prepared coming to class having read module 22, because we'll take our module 22 reading quiz, and then do some vision stations, dig into that. And then by Monday, you will be taking your matching test that looks at, again, this ear, as well as a diagram of the eye, which we will go over on Friday. Okay, so happy Flex Day. If you have questions, feel free to reach out. We will touch base on like test corrections and things at some other point in time. Just hang tight, get this work done, stay on top of content. That's the goal. Okay. Awesome. Thanks, guys. Have a great day.